In this video, we discuss exercise 48 from the Larson Calculus text, 10th edition. It just gives us a good opportunity to discuss rates of change that are related to each other, also known as related rates, in a real-world application. So we've got some numbers, some data that they're given in the table below. The table shows the number in millions of single women S and married women M in the civilian workforce in the US from 2003 through 2010. We'll let T equals 0 correspond to the year 2000. So T equals 3 is 2003, T equals 4 is 2004, and then as we increase, eventually we get to T equals 10 in 2010. And this S represents the number of single women that are working in the workforce, or that are in the workforce in millions in that particular year. So this particular data point represents 2008. It says in the year 2008, there were 20.2 million single women working in the US in the civilian workforce. And there were 37.2 million married women working in 2008. So that's how we interpret those numbers. And the first thing we'll do is we'll find some linear models for those numbers. So basically, we're just trying to find an equation of the form y equals mx plus b for these two variables, but we're using m for the number of married women in millions in a particular year that are working, and then we're using s for the number of single women that are working. So we don't want to use m and b. We'll just use a and b for our coefficients. So I want S to be represented by this linear model. So I'll have some constant times t plus some constant. I'll use a sub 1 and b sub 1 for the slope and the y-intercept of that function. And we're just basically using the computer to do the linear regression to find the coefficients that relate this S to this, the S, which is the number of single women that are in the workforce and corresponding to a particular year T. And it turns out that if we look for that linear model, our constant A, the slope for the number of working single women in the US, and year T is this A equals 0.316167 approximately, and then B equals 17.49. And then we do the same thing for the number of married women working, and we get a different slope, 0.201 is the slope for the number of married women, and 35.2 is the y-intercept for the number of married women. So we've got these two lines, or these two sets of points. One thing that I want you to notice right away is the number of single women is this set of orange dots, and the number of married women is this set of teal dots. There are a lot more married women than there are single women in the workforce during these years, according to the data from the table in the textbook. Then we can find a line that fits through those points. Desmos.com is doing most of the work on that. We just say, I want a linear model, so I want S to be a function of t, and I want it to be a constant times t plus a constant, and then Desmos finds those constants for us. And we want the same thing for m. Now for each of these, we want to be able to interpret the y-intercept and the slope. So the y-intercept is relatively easy to interpret. T equals 0 corresponds to the year 2000. So when we look at that y-intercept for this function S, where S is the number of married women, or excuse me, single women working in a particular year, when T equals 0, we get this 17.49. So what that tells us is that 17.49 million women were working, million single women were working in the US in the year 2000, according to the model. Now the model is based on data from 2003 till 2010. So it's just extrapolating, going backwards. We're saying, assuming that this trend holds outside of the years 2003 through 2010, then we would expect that if we went backwards, that there would be 17.5 million single women working in the year 2000. And similarly, for the number of married women working in the year 2000, the model says that we've got about 35.2 million married women working in the year 2000. Now the slope is, remember, it's a rate of change. It's a rate of increase because our A values, our slope values are positive in both cases. So when we see this A equals 0.317, the way we can interpret that is that there are 0.317 million single women added to the workforce each year, on average, based on this linear model. So if we multiply by 1 million, that tells us that there are 317,000 additional single women added to the workforce according to this model each year. And then there are an additional 201,000 married women added to the workforce each year according to the model. Actually, I think I may have got that backwards. The slope for this one, for the purple line, is that 0.317. So that's 317,000 additional women are added to the, or additional single women are added to the workforce each year. And the slope for this one is that 0.201, which means 201,000 additional married women are added to the workforce each year. So we might say that that rate of increase is very small because it's just it's a fraction. But when you multiply by 1 million, we're talking about, 200 million women, or 200,000 women, or 300,000 women. It's a lot of women being added to the US workforce each year. Okay, so that's that. And you say, okay, well, how are the rates of change of S with respect to time and the rates of change of M with respect to time related to each other? In order to figure that out, we might make a model that relates S and M. So this is actually part of the problem statement in the book. At first, I didn't think this data set was particularly interesting, but I did think, ultimately gives us a good opportunity to discuss rates of change. So here's what the problem statement in the textbook says. It says, use the regression capabilities of a graphing utility to find a cubic polynomial modeling M of S, the number of married women, working women, as a function of the number of single working women. Let time t be measured in years where 2003 corresponds to t equals 3. Okay, so using the same data set as before, I want to plot my S values and my M values together. So there's no t-axis here. This is M on our vertical axis and S on our horizontal axis. We want to actually, we can label those S of t and M of t because those depend on years. We plot the points, that's what we get. And then if we want a cubic model, I want my M to be a constant times S cubed plus a constant times S squared plus a constant times S plus a constant. The computer, the Desmos.com graphing utility, is actually finding those coefficients A, B, C, and D so that this cubic function fits the data that we have. And when you look at these data points, it looks kind of cubic. It looks like it's decreasing and then increasing and then decreasing again. So when I draw that curve, it does kind of fit. So I'd say, okay, it looks like a cubic model. Like, gosh, what does that mean? Let's look at this table of values again. Notice as we go from 2003 to 2004, 2005, and so on, the number of single women in the workforce increases. Not by very much, but we've got 18.4 million, 18.6 million, 19.2 million. And you might say that, that 0.2 or 0.6 or 0.3 increment as you go from here to here doesn't sound like very much, but when you multiply by 1 million, you're talking about 200 million women, 500 million women, 300 million women, and so on, depending on that increment. So it's actually a larger increase in the number of women than you might initially think. But as we go from year to year, our S values increase. So the number of single women working every year increases, with the exception of 2008 to 2009, that stayed the same, according to the data in our table. At the same time, the number of married women was fluctuating a little bit, went from 36 down to 35.8, and 35.8 up to 35.9, and then it increased to 36.3, increased to 36.9, increased to 37.2, increased to 37.3, and then decreased to 37 or 36.7. And so we get this cubic function. So I just type m sub 1 tilde and then the model that I'm looking for, and I'm using m sub 1 and s sub 1 because those are the variables from our, from our table of values up here. I chose s sub 1 and m sub 1 so that I could use s and m as variables that were, different from those from the data set. But the values of A, B, C, and D are automatically stored by Desmos. I just wanted to show you what those were. So it automatically stores those values. But if you want to see them, you can just type A equals, B equals, C equals, D equals, and you can see the values. It's saving a lot of decimal places for that A, B, C, and D. And so our model, where M is the number of married women in the workforce in millions as a function of the number of single women in the workforce, is this AS cubed plus BS squared plus CS plus D. I'm like, I really don't know how to interpret that, like thinking of the number of married women as a function of the number of single women and thinking of that fluctuation. I'm like, I don't really know if that's really appropriate, but there is a relationship, as we can see, and a cubic model seems appropriate. If we look at the R values, that R squared is 0.9783. If that number is close to 1, that means it's good. I won't get into the details of what that means. I actually don't remember it very well, but it means it's a relatively good fit if that number is close to 1, and it is close to 1. And so we have that as our model. And then we're asked in the textbook to find dm/dt. So that is the change in married women in the workforce per unit time, or per year in particular, in millions. Then we're asked to use the model to estimate dm/dt in 2007, given that it was predicted in 2007, the number of single women in the workforce would increase at a rate of 0.75 million per year. While it's relatively easy to compute that, we're just going to use the power rule to take the derivative of this with respect to s, and then we'll multiply by ds dt. And the ds dt in this case, it says in 2007, the number of single women in the workforce increases at a rate of 0.75 million per year. So that just tells us ds dt is 0.75 million, or 0.75, as if we just look at the number part. So let's do some computation on paper. So this is super easy, relatively easy to do. A, B, C, and D are constants. So the derivative of this with respect to s is just 3 times a times s to the 1 less power. So we have 3a squared plus 2b times s, because you're taking that 2 down, 2 times the b is your coefficient, then you have s to the 1 less power, and the derivative of a constant times s is just a constant, and the derivative of the constant itself is 0. So the derivative of m with respect to s is given by this function, which if I substitute in the a values, where a is this approximately, b is this. This is our c, well, that part of it is our c, and that's our d. If I substitute in a, b, c here, this is what I get for my m prime. And dm/dt is just the derivative of the outside function evaluated at the inside function times the derivative of the inside. So I want the rate of change of m with respect to s, which can be written this way in Leibniz notation, times the derivative of s with respect to t. So we just have this function here, and a, b, and c are stored by our calculator, and we're taking that function and we're multiplying it by ds dt. Now we were asked for dm/dt in the year 2007, so that is when t is equal to 7. In order to find that, we take this derivative, the change in m with respect to s, and then we evaluate it at s, evaluate it at t equals 7, and then we multiply that by the derivative of s with respect to t when t equals 7. The s value when t equals 7 can be found in our table. When t equals 7, that corresponds to the year 2007. Our s value is 19.7. So I want to substitute 19.7 into this function here, replace all of my s's with 19.7s. That's going to be a number, and then we'll multiply that by this ds dt, and the ds dt was given to us in the problem statement. We were told that this is 0.75. So what we end up with, if I use prime notation rather than Leibniz notation, is m prime evaluated at s of 7 times s prime of 7. S prime of 7 is the 0.75. This is m prime evaluated at 19.7. And we're going to multiply those two together. So we have 0.75 times this function evaluated at 19.7. That's a number, and we'll have some interpretation for that. Okay, so our derivative of our model is m prime of s. I had to type that in manually, so I just wrote m submodel prime to define, or as the definition of my derivative function. And so I just got 3a times s squared plus 2b times s plus c. So that's a function of s. And if I substitute in 19.7 for my s value and 0.75 for my ds dt, that is the value of dm dt. And it's giving me problems here and here. Can't use s1 as a parameter because you're using it for something else. Okay. I think I changed the rules of s and s1 at some point. So if we change the rules of s and s1, this comes out to be well-defined, and then we can substitute in s equals 19.7, and we get this number is 1.225. Uh, 1.226 if we estimate. You might say, okay, now we've got all of these different numbers. What's our interpretation of them? Well, I think it would be helpful if we could actually see that derivative function. Let's zoom out a little bit. There's the derivative. Way down there. And say, okay, well, what does that mean? That's our m prime as a function of s. So as at two particular s values, our m prime is 0. And then in between those two s values, our derivative is positive. So the rate of change is increasing, and then the rate of change reaches a maximum, and then the rate of change is decreasing. But before that, the slope is negative, and it's very, very negative, and it gets less and less negative and less negative, and then it's 0. Then it becomes positive and more positive and more positive until it gets to a maximum positive slope. And then it starts decreasing. It goes from going from a maximum positive slope to a smaller positive slope and a smaller positive slope until it has a 0 slope. And then the function starts decreasing again. You can think of that, or it's easier to see if you could see this and the original graph at the same time. So I think I'm just going to add like a huge number to it. Let's see. I want it to be up here near 40. So let's just add 30 to it. Now let's add like 50. You're like, you can't change the values of the function. I know. I'm just trying to get a sense of the slope. That doesn't work. What I was trying to help you see was where those zero slopes were. So we'll zoom in a bit. So the rate of change of m with respect to s is 0 here and here. The function is decreasing until we get to this s value, and then it's increasing here, and then it gets to a maximum slope in the middle. We call this a point of inflection, when the slope goes from positive and increasing to positive and decreasing. So it's when the rate of change actually changes direction. So it's positive. It goes from a zero slope to having a small positive slope, a larger positive slope, a larger positive slope. Then here it has a very large positive slope. Then it has a much smaller positive slope and a much smaller positive slope. And then it has a zero slope. And then it has a negative slope and a very, very negative slope as you go this way. So you can kind of imagine that you're going to have a zero value here and a zero value here, positive values in between with a maximum that corresponds to this location, that S value. And you have negative slope on either side. So what you end up with is this sort of parabola that's like graphed like this. Of course, it's down much, much farther. But that's sort of the relationship that you would expect between this cubic function and its derivative. But it's way, way down here because the constant term itself is, well, the number that we're adding is actually pretty small. Well, maybe I'm wrong. I'm actually subtracting something relatively large. Let's look at the equation itself. So our m prime is this. So I've got this quadratic, but then I'm subtracting 1,416 from it whenever I take the derivative of this with respect to s. And so I get this. You say, well, what is that? Well, if you look at the units, this is the instantaneous rate of change. Of the number of working married women as the number of working single women increases. By 1 million. It's going to be 1 unit change in S, but S is measured in millions. So if I plug in a particular S value here, that's going to tell me the instantaneous rate of change of the number of working women in the workforce as the number of single women in the workforce increases. So when we evaluate M prime at S of 7, what we're saying is in the year 2007, there were a particular number of single women working in the workforce. And it turns out if we look at our table of values, when we were in the year 2007, there were 19.7 million single women working in the US. I said, well, how does M change as S changes? When S is 19.7 million working women, how does the number of married women change? Well, to find that, you just find M prime and evaluate it, M prime of S, and evaluate it at S equals 19.7. I'm saying S of 7 here, though, because we're also tying it back to the year 2007. So S, this number of single women working, is a function of time, and the number of married women is a function of the number of single women. So we've got the number of married women as a function of the number of single women, which is a function of the number, or a function of the year. And so that's why we've got this composite function, M prime evaluated at S of 7. So that's this number right here. Now, if we go back to our calculator on Desmos.com and we just evaluate our derivative at 19.7, we see that this value is approximately 1.63. So this number is 1.63, and you might say to yourself, well, what does that mean? Well, that tells me that 1,630,000 additional married women began working in 2007 as the number of single women increased, and the number of single women in the workforce increased from 19.7 million to 20.7 million. So they're saying for a 1 million change in the number of single working women, there are 1.63 million married women that are added to the workforce. So the number of single women increases by this much as the number of married women increases by this much. And that was true momentarily in 2007, and that's what this number is. So this is a number of married working women per number of single working women. And then if I want dMdt at t equals 7, which is the rate of change of the number of married women working with respect to time, so per year in the year 2007, I'm just going to take the rate of change of this and multiply by the rate of change of that. So this is a number of working married women per number of working single women, and then we're going to multiply by the number of single, or the rate of change of the number of single women working per year in the year 2007. So we're told that that was 0.75 million. So as we go from 2007 to 2008, about 750,000 additional single women were added to the workforce. So you say, okay, well, what does that mean when I multiply those together? When I multiply those together, I get this number 1.226, which tells us that the rate of change of the number of married working women with respect to time in the year 2007 is 1.226 million. So 1,226,000 approximately married women were added to the workforce in 2007. As we went from 2007 to 2008, that rate of change, that instantaneous rate of change, is that 1.226. That's it. I like this problem because it's an opportunity to discuss rates of change and how different variables are related to each other. I'm still not sure about relating the number of single women working in the workforce to the number of married women working. It just feels a little bit weird to me. I don't know why that particular relationship was chosen, but the textbook authors chose it, so I decided to explore it. If you have a better interpretation or a better reason for why we would study the relationship between single working women and married working women, let me know. But that's the model that they wanted us to use in the book, and we can see that the rate of change of the number of married women working per year is related to the rate of change of the number of single working women per year by this extra factor, which is the change in the number of married women working as the number of single women working increases. And so it's basically just another example of the chain rule, and it shows us how these two rates of change with respect to time are related to each other.